Hi everyone, my name is Jobin Thomas Valliyakalayil and I'm a PhD student at Australian National University. Today I'll be talking about my work on enhanced frequency noise reduction for LISA using two stable references. One is the onboard optical cavity and the other is the interspacecraft separation or the arm of the interferometer. Now, for almost all laser interferometry work, reduction of laser frequency noise or laser stabilization is a critical component. For LISA's sensitivity goal of 10 picometer per root hertz, we need to have 14 orders of suppression from free running laser. As a result, multiple laser stabilization techniques needs to be deployed concurrently in order to meet this requirement. One of them is the cavity locking, which is realized through the bound river hall locking scheme. Using the cavity locking, we stabilize the laser with respect to a resonant optical cavity. Another laser stabilization technique is TDI or time-delay-interferometry. It is a post-processing technique in which we apply appropriate delays to the phase measurements and hence we make a Michelson response. Different generations have been developed and analyzed, and currently the second generation TDI, which can suppress up to 8 orders, is in the LISA baseline. Even though TDI is a powerful technique, it is difficult to verify the sensitivity requirement on ground without the complete complexity of the system in space. So there is a potential risk factor in which if TDI fails to meet the requirements, we might lose out gravitational wave data. As a result, the motive of this research has been to re-examine arm locking stabilization in order to relax TDI requirements without any with minimal hardware changes to the LISA basic structure. So looking at previous literature on arm locking, we start off with the single arm locking where we stabilize the laser with respect to a single arm of the interferometer. Most schemes have also been developed that utilizes both the arms of the interferometer, and their integration with other pre-stabilization has also been analyzed. However, none of these techniques are compatible with the current baseline design of LISA, as it either requires additional modulation or a tunable cavity length. Another challenge of implementing arm locking is the phenomenon of Doppler pulling. It occurs when the received light is shifted by a Doppler bias due to the relative velocity between the spacecrafts. Due to the nature of the arm sensor, the Doppler shifts gets integrated over time, thereby causing potential problems by pulling the laser frequency. So in the research, what we're doing is we start off with the baseline structure of LISA, in which we have the cavity locking scheme given by the PDS sensor, and we also have the arm measurement, which is the interspacecraft measurement readout given by the space meter, and we will develop a complex controller scheme that can be implemented completely digitally or with some or minimal analog electronics, and use both the PDS sensor and the arm sensor to feed back to the laser. Such a complex controller will ensure that we use the best parts of both the sensors in order to stabilize the laser. So the requirements for such controller is given in this slide. The first is a frequency sharing with the sensors. The arm being more stable than the cavity will be dominant in the LISA science band, while at other frequencies we have the PDS sensor being dominant. At higher frequencies, due to the flat response of the PDS sensor, we get better phase margin statistics. And at lower frequencies, to reduce the effect of Doppler pulling, we have the cavity again dominant again dominant at lower frequencies. But even if Doppler pooling persists, we also have an additional requirement that the effective or residual Doppler pooling would be within 1/10 of the line width of the cavity, which in this case is around 200 kilohertz. And so to make sure that the cavity maintains its lock, we require that the Doppler pooling is less than 20 kilohertz. So with these requirements, we have designed an appropriate controller, and its body plot is shown in this figure. The red trace shows the combined response, with the blue trace showing the arm contribution and the yellow trace showing the cavity contribution. The data points given in the plot illustrate the phase margins at the critical points of crossover, while the shaded regions shows the dominance of each sensor in the frequency band. So one of the first metric that we use to measure the performance of the system is the noise characteristics. Here we compare the noise performance with the first generation TDI requirement. As I mentioned earlier, in order to relax the stringent requirements on TDI, we compare the noise characteristics to the TDI requirement itself. So by comparing it to the first generation TDI, we give sufficient margin to TDI in order to, we give sufficient margin to TDI and help ease the any stringent requirements on it. So the total noise profile is given by the dashed blue line, which is around 2 orders lower than the TDI requirements at around 10 millihertz. Additionally, I've also plotted out the LISA requirement cavity noise, which is given by the dashed red trace, and the equations of the TDI and the cavity requirements are given in the right-hand side. Another performance metric that we will be looking at is the effective Doppler pooling, which can be thought of as the step response of the system to Doppler shifts. The Doppler shifts in the system is considered to be a combination of sinusoids with 1 year and a half year periods. And we assume that at the moment of locking, we will have a second order polynomial approximation using the Doppler constant, the Doppler rate, and the Doppler acceleration to mimic the behavior of the Doppler shifts. So with this these equations, we look at the effective Doppler pooling as shown in this figure. The different traces corresponds to different set points during the LISA mission, during the spacecraft motions, during the spacecraft orbits, at which we can show that at any given point, whenever the arm controller is turned on, provided that the Doppler requirements or the Doppler parameters have the sufficient precision, the Doppler pooling will be within the requirements of the cavity. In order to achieve the precisions for these Doppler parameters, we propose that we use 2 onboard measurement schemes. One is the inter-spacecraft interferometer link, and the other is the ranging measurement using pseudo-random noise modulation. So for further information and a detailed analysis of the controller, please refer to the journal article given in PRD. The link is given in this slide. And for future work, we aim to do an experimental setup to verify this control scheme, in which we use fiber delay lines as the arm sensor and a cavity similar to the graceful on, it will be also used for the PDS sensor. We will also look at potentially more complex sensors in order to reduce Doppler pooling and to improve noise budget. Thank you so much for listening. If there are any questions, please feel free to reach out.